All right. So now we have this new tool, which is if you want to show convergence of a series whose terms are not necessarily positive, and maybe it's not alternating, it's not the simple case of an alternating series. What you can do is turn everybody into a positive number by taking absolute values of your individual terms, and then try to show that this series, which now has positive terms, is convergent. In other words, try to show absolute convergence of your series. If you can do that, then we know that absolute convergence definitely implies convergence. It's even stronger. Absolute convergence is one level stronger than the regular convergence. Okay. Uh, this idea, when you go back and think about the ratio test and the root test that we talked about, uh, gives us the following version of the ratio and root test for series sigma an in which an is not necessarily positive. So remember, before, like maybe 10 days ago, last lecture before the review, what we did was we had a series sigma an in which an was positive, and we applied the ratio test. We formed an plus 1 over an. We took the limit. If the limit exists, we called it L. Then the ratio test said if L is less than 1, series converges, greater than 1 diverges. If L is equal to 1, inconclusive. And the similar thing for the root test. Now here, if an is not necessarily positive, if this series an is not necessarily does not necessarily have positive terms, what I can do is I can take absolute value of an, and now I form absolute value of an plus 1 over absolute value of an, which is the same thing as absolute value of the whole thing, an plus 1 over an. And now I take the limit of this, I call it L. In other words, I'm applying the ratio test not to sigma an, but to sigma absolute value of an. And what comes out of the ratio test in this case is that if this L is less than 1, my series is absolutely convergent and therefore convergent. So I'm in good shape, just like the regular ratio test. If L is greater than 1, my series with the absolute value sign diverges. But you can show that in this case, the original series must diverge too, because in this case, the general term doesn't even go to 0. The general term goes to infinity. So L greater than 1 implies divergence, and L equal to 1 inconclusive. That's why I put question mark, meaning that if you're so unlucky as to get L equals 1, then you have to sit down and treat that case using a different method. And the same thing for the root test. Instead of the usual root test for the case an positive, where you take the nth root of an, now take the nth root of absolute value of an. Take the limit, call that L. If L is less than 1, your series is absolutely convergent and therefore convergent. And if L is greater than 1, your series diverges. And if L is equal to 1, um, it's your unlucky day. You have to think of a different method. All right, enough of the general statements. Now let's focus on problem solving. So I'm going to give you a bunch of examples, and we're going to sit down and figure out what to do. You see, in the first example, I definitely have an alternating series. Because of this term, the rest of it is positive. You see, this is positive. And in front of it, I have this alternating pattern of plus 1, minus 1. So this indeed is an alternating series. And if you can show, and your Bn is this, you can actually show that this Bn is eventually decreasing. Maybe in the beginning for the first few n, it acts crazy, but then it falls into this decreasing regime. And it does indeed go to 0, because even though n to the fourth goes to infinity, the bottom, which is exponential, 5 to the n, goes to infinity way faster. The top goes to infinity like a polynomial. The bottom goes to infinity like an exponential. So the bottom will take over. The top can't keep up, and the ratio will eventually go to 0. So it is possible to look at this example and say, yeah, by Leibniz test, this must converge. But I want to show you that the ratio test tells you something more. So let's see. So we apply the ratio test. Usually the ratio test is the simplest, the most convenient, most straightforward test, as we will see in the upcoming examples. So what is your AN? This is your AN, right? This is your AN. So since this is the first example, I'm going to write everything, so bear with me. But as we gain a little bit of experience, we're not going to spell out every single step like that. So when you take absolute value, you essentially kill this term. So when you take absolute value of AN, it's absolute value of this times absolute value of this. This part is positive, so it's itself. And this portion, when you take absolute value, is just 1. So that's absolute value of AN. So L, which is the limit as n goes to infinity of absolute value of AN plus 1. Why am I putting absolute value? Because my series does not have positive terms. If you're working with series with positive terms, like we did before the review, you don't need to put absolute value. So now the best way that I find this method much easier in terms of writing, I'm going to put absolute value of AN plus 1 here. And then instead of forming this nasty fraction AN plus 1 here, and then on the bottom putting absolute value of AN, I just put AN plus 1, which is n plus 1 to the fourth over 5 to the power n plus 1. That's absolute value of AN plus 1. Instead of dividing it by absolute value of AN, I multiply it by the reciprocal, which is times 5 to the n over n to the fourth. You see, this way, I don't have to work with like outrageously complicated fractions, a big fraction on top of a big fraction, and then try to simplify things. This is much cleaner, writing it this way. And now, this, as you can see, I can simplify. For example, I have 5 to the n here, and 5 to the n plus 1, which is 5 to the n times 5 to the first, or 5. So I can cancel this with this, and that leaves a 5 here, an extra 5. So this is the same as the limit, as n goes to infinity of, I have a 1/5, because I have a 5 on the bottom, and I have n plus 1 on the top and on the bottom, n plus 1 to the fourth on the top, n to the fourth on the bottom, which I can combine as n plus 1 over n to the fourth. Now, can you tell me what happens? So this is a fixed number as n goes to infinity, and this is a fixed exponent. What happens to n plus 1 over n as n goes to infinity? What is the limit of n plus 1 over n? Exactly, it's 1. And since this is a fixed exponent, it's not going to infinity or anything. It's just 1 to the fourth, which is 1. So maybe I can write it as 1/5 the limit as n goes to infinity. If you want to know why that limit is 1, just break it as n over n plus 1 over n. So if you split it like that to the power 4, then you see that this thing will go to 0. As n goes to infinity, it goes to 0. So this is 1 to the fourth, which is 1. And you get 1/5 as the final answer, which is less than 1. So it's our lucky day. Lucky that we didn't end up with answer 1, because that would be inconclusive then. So that means the series is absolutely convergent, therefore convergent. So the advantage of applying the ratio test here, as opposed to the alternating series test, if you wanted to do the alternating series test, the Leibniz test on this example, you would have to actually show that this sequence, n to the fourth over 5 to the n, is eventually decreasing and it goes to 0. That requires a little bit of work, but even after that, you could only say that the series converges. But here, using a much simpler argument, we showed something stronger. We showed that not only is this series convergent, it's absolutely convergent, which is something even stronger. Now, let's take a look at this next example. For what value or values of x is this series convergent? This is going to be the type of series in terms of a variable x that we'll be talking about soon. This would be an example of a power series. A power series looks like an infinite polynomial. So a polynomial is a finite sum of powers of x, non-negative integer powers of x. But in a power series, you have infinitely many terms instead of finitely many. So for example, if you wanted to, let me just write it here. If you wanted to expand this, it would be x to the power 0 over 0 factorial, which is just 1. And then x to the first over 1 factorial, which is x over 1. And x squared over 2 factorial, which is x squared over 2. X cubed over 3 factorial, which is x cubed over 6, etc., etc. So it's an infinite sum containing powers of x. That's why it's usually called a power series. But I don't care for now what this is. I don't concern myself with the exact meaning of this. We'll discuss that later. Right now, the only thing I focus on is this question. Somebody gives me this infinite series. This is my general term an. And I know that the most powerful and versatile tool that I have to study such a thing is the root test, is the ratio test or the root test. But you can actually use either of them, but the ratio test is even easier. So if you were to form L, which is the limit as n goes to infinity of absolute value an plus 1 over an. Again, why do I put absolute value? Because I don't know if these guys are positive or negative. The bottom is always positive, but depending on what x is, x to the n could be positive or negative. So just to be on the safe side, I put absolute values. I don't have a series with positive terms. So this will be the limit as n goes to infinity. Again, the same trick. I put absolute value around everything unless the thing is already positive. So when I put absolute value around this, It's just putting absolute value around x to the n, which is the same thing as absolute value of x to the power n. And n factorial doesn't need absolute value because it's already positive. So absolute value of an plus 1 will be absolute value of x to the power n plus 1 over n plus 1 factorial. That's like the top of this fraction, absolute value of an plus 1. And then instead of dividing it by absolute value of n, I multiply it by the reciprocal of it, which is n factorial over absolute value of x to the n. And now look at the cancellation that you have here. Absolute value of x to the nth power and absolute value of x to the n plus first power, they cancel out and they leave only one absolute value of x on the top. And this guy cancels n factorial, simplifies with n plus 1 factorial. It leaves only a factor of n plus 1 on the bottom. Because n plus 1 factorial is the product of all numbers from 1 up to n plus 1, which is the product of all numbers from 1 up to n, namely n factorial, times n plus 1. It has only one extra factor. And what this means is that this is simply the limit as n goes to infinity. The only thing that survives is one absolute value of x on the top and one n plus 1 on the bottom. Now, for any given x, can you tell me what this limit is? For any fixed number x, what happens to this expression as n goes to infinity?
Goes to 0.
It goes to 0. Very good. Because the top is not moving. You don't see any n on the top. It's a fixed number. Don't tell me that it's x and x can move. Well, fix x for a moment. For a given x, the top is fixed, and the bottom is going to infinity, so the whole thing goes to 0. So this is equal to 0 for every x. No matter what your x is, this limit L is always 0. What's the conclusion? What do you conclude? When your L is 0 in your ratio test, what's the conclusion? It's absolutely convergent. Very good. So the series let me get this out of the way. So the series is absolutely convergent for every x. In other words, for what values of x is the series convergent? For every value of x. Doesn't matter. No matter what your x is, this series will converge. And very soon, namely 2 lectures from now, we'll see that if you compute the, so we know that this series converges. If you compute the sum, it's exactly e to the x. In other words, this power series represents the function e to the x. E to the x itself is not a polynomial, so you can't write e to the x as a polynomial, but you can write it as an infinite polynomial, something like a polynomial with infinitely many terms. And that's a powerful, powerful idea. That's the idea behind the Taylor series of a function. But let's not get ahead of ourselves. For now, our task and our ambition is very limited. I give you a series, you apply the, say, the ratio test on it, you determine where it converges or diverges. Same question for this. You see, this is another example. So next question is another example of what I would call a power series. It's an infinite series. It's just some stuff times x to the n. So this stuff depends on n. It's like, I don't know, Cn x to the n. So when you start at n equals 1, you can compute the coefficient of x to the first, which is x. And then for n equals 2, you compute this coefficient. That's going to be the coefficient of x squared, and then the coefficient of x cubed, and so on and so forth. If you apply the ratio test, similarly, you have to form an plus 1 over an in absolute value. And there are a bunch of simplifications that you can make along the way to make your life easier. Remember, this is my an. This is my an. I have to take its absolute value and put it in this formula. When I take absolute value of this expression, it's absolute value of this, absolute value of this, and absolute value of this, because absolute value of a product is product of absolute values. Absolute value of this part is the same as absolute value of x to the n. The bottom doesn't need absolute value because it's already something positive. And what happens to this guy as I take absolute value? It turns into 2 to the power n. If you have minus 2 to the power n, you take its absolute value, it's just 2 to the power n. So with that in mind, the overall effect of taking absolute value of this for an plus 1, I would be getting, so absolute value of an plus 1 would be 2 to the power n plus 1 on the top, absolute value of x to the n plus 1 on the top, and then fourth root of n plus 1 on the bottom. That's absolute value of an plus 1. And then instead of dividing it by absolute value of an, it's much easier to multiply it by its reciprocal, which is fourth root of n divided by 2 to the n absolute value of x to the n. This looks like a mess, but if you take your time, you see that it's very easy to simplify this. 2 to the n on the bottom and 2 to the n plus 1 on the top. They leave a 2 on the top. X to the n on the bottom, x to the n plus 1 on the top. They will leave absolute value of x on the top. It is imperative that you not forget putting absolute value around x. Don't replace it with x. And then I have fourth root of n on the top, fourth root of n plus 1 on the bottom, which I can combine into fourth root of n over n plus 1. So the overall after simplifying, the overall expression will be 2 absolute value of x times n divided by n plus 1. Fourth root of n over n plus 1, I can write as n over n plus 1 to the power 1/4, because drawing this big radical is complicated. OK, by the same reasoning, n over n plus 1 goes to 1. I'm raising it to a fixed exponent. It's important. So it's going to be 1 to the power 1/4, which is 1. So this limit will be 1. And in the end, I only, so this limit this tends to 1. So in the end, I get 2 absolute value of x. That's my L. That's my L. And now, depending on what x is, L is less than 1 or bigger than 1 or equal to 1. So if I want this to be, so this is less than 1. Let me write it this way. That's my L. And L depends on the size of x. So I can say that if I have absolute convergence if 2 absolute value of x is less than 1. Remember, that was my L. But what's the meaning of that? 2 absolute value of x being less than 1 means absolute value of x is less than 1/2. That means the distance between x and 0 is less than 1/2. So that happens if and only if x is in the interval 1/2 to -1/2. That's where, if you are in this interval from -1/2 to 1/2, your absolute value is less than 1/2, and therefore twice your absolute value is less than 1. Therefore, your L is less than 1. Therefore, your series is absolutely convergent. So in this infinite series, if I pick my x, any value in this interval, the ratio test shows that this series will be absolutely convergent, therefore convergent. On the other hand, it will be divergent if twice absolute value of x is greater than 1, which means absolute value of x is greater than 1/2, which means either x is greater than 1/2 or x is less than -1/2. If your distance to the origin is greater than 1/2, either your x is greater than 1/2 or less than -1/2. So let's take a look at the what we have achieved so far. What I have shown so far, let me add a page here just to make sure I'm not running out of space. So what I have shown so far is that if I stay in the interval from -1/2 to 1/2, I have absolute convergence. This is the x-axis. And if my x is greater than 1/2, or if my x is less than -1/2, I have divergence. So along the x-axis, in this interval around 0, 0 is somewhere here. In this green interval around 0, I have absolute convergence, therefore convergence. And if my x is picked from the red intervals, from 1/2 to infinity or from -infinity to -1/2, I have divergence. Now, what's left to be studied is what happens exactly at these 2 points, at the endpoints of the green interval, what happens? So I have 1 point here. This is what happens at, so what happens at these 2 points? So we have to study them separately. So when x is 1/2, go back to your formula. This was the formula for the series. Let me copy that. Put it here. And substitute 1/2 for x. So it's going to be 1/2 to the power n. In other words, you have 1/2 to the n. Right? This is what I get. And when you simplify this, you have a 2 to the n on the bottom, 2 to the n on the top. You get sigma n from 1 to infinity. You're left with -1 to the n on the top and 4th root of n on the bottom, because this 2 to the n on the bottom cancels the 2 to the n on the top, so you have minus 1 to the n on the top left, and this guy on the bottom. And this is an alternating series with Bn equals 1 over 4th root of n, which is decreasing going to 0. So this is convergent by Leibniz. So what that means is that I can take this and basically fill it green. I have convergence here. But I couldn't do that using the root test, because that's the case L equals 1 in the root test. So I had to go back and do it by hand. What about at x equals minus 1/2? Let me try to copy this to save time, because the formula is very simple. They're similar. So here what you have is minus, and now minus 1/2 to the power n and minus 2 to the power n completely cancel out, and you have only 1 here on the top. Now, can you tell me the fate of this infinite series? What is it? Convergent or divergent? 1 over 4th root of n. Sigma 1 over 4th root of n. Convergent or divergent? What do you think? It's one of the standard cases that we've seen before, because remember, this is sigma n from 1 to infinity of 1 over n to the power 1/4. So this is a p series where p is 1/4. So this is divergent, because it's a p series with p equals 1/4, which is less than 1. 1 over n to the 1/4, or 1 over 4th root of n, diverges. So that means I can go back, and in my investigation on this diagram, I can paint this red, because at negative 1/2 it's divergent. So this is a full picture. This is a full picture of what happens to this infinite series at every point x along the real axis. Green means convergence, and red means divergence. So time is up. So let me just show you this last slide, which sets the stage for what's about to come next lecture. So the fact is that, so you see here, I found some interval around, in this example, I found some interval around the origin. The size of this interval, the radius of this interval was 1/2. So take the origin, go 1/2 to the right, 1/2 to the left. In that interval, you have convergence. Away from that interval, you have divergence of that power series. This is a general phenomenon. And the general phenomenon is that for a power series, sigma Cn x to the n, where Cn are a bunch of coefficients, there is a number r called the radius of convergence, such that the series is absolutely convergent if your distance to the origin is less than r, and it's divergent if your distance to the origin is greater than r. In my last example, the radius of convergence r was 1/2. So the picture is there is some interval around the origin of the radius r, which means take the origin, go r to the right, r to the left, that's your interval, from negative r to plus r. On that open interval, you have absolute convergence. Away from that, you have divergence. And what happens at these two exact endpoints, you have to study that on a case-by-case basis. Nothing can be said in general. You have to take a look at each individual example to make a decision. This number r, the radius of convergence, depends on these coefficients. So depending on what the coefficients are, you apply the root test or ratio test, and you find r. This picture shows the case where r is a number between 0 and infinity. There are two extreme cases. If the radius r is infinity, then it's like pushing this green all the way to the real line. Everything is green. So the radius of convergence here is infinity. The series will be absolutely convergent everywhere. This is like my first example here. This example, you remember this example? It was L was 0, independent of x, so the series was absolutely convergent for every x. That's the extreme case where you have convergence everywhere. So in terms of this radius of convergence terminology, you can think of it as the case where the radius of convergence is infinity. So the green will cover the entire real line. The other extreme is it could happen is when r is 0. This radius of convergence can be 0, in which case the green interval will collapse into just a single point 0. Obviously, this series will converge at 0. When you plug in 0, only the first term, C0, the constant term, will survive. The rest of the terms will be 0. So such a power series always converges at this center, 0. That definitely is always a green point. When the radius of convergence is 0, that's the case where nothing else is green. So that interval around the origin will collapse into just the origin. This would be, next time I will start the lecture by giving you an example of this case. You could have a power series in which r is 0, and that power series will not converge anywhere except at the origin. If you move away from the origin just a tiny bit, the series will diverge. So that's the general picture that we should have in mind when it comes to convergence of power series, and I will continue this on Thursday. Any questions? All right. So take care, guys. I'll see you on Thursday. Be safe. You're welcome. You're welcome.